Imagine standing on a hill beneath a clear night sky, staring into the endless expanse of stars. You might think you're seeing the universe as it truly is, but you're not. What you see is only a sliver of what's really out there. In fact, the stars, planets, gas clouds, and galaxies, the entire visible cosmos, make up less than 5% of the universe. The rest? It's invisible, untouchable, yet it exerts gravitational force on everything. We call it dark matter, and though we can't see it, it holds the universe together. This is the story of a ghostly substance more powerful than anything we've ever known, and the hunt to uncover its true nature. Our journey begins in the early 20th century. Astronomers were mapping galaxies and measuring their motions. One of them, Fritz Zwicky, was studying the Coma Cluster, a dense group of galaxies bound together by gravity. According to Newtonian physics, the speed at which the galaxies orbited the cluster should correspond to the amount of visible mass in the form of stars. But the galaxies were moving far too fast. By all logic, the cluster should have flown apart, yet it held together. Zwicky proposed a radical idea. There must be more mass than we can see, dunkel materia, or dark matter. For decades, Zwicky's theory was largely ignored. Then, in the 1970s, American astronomer Vera Rubin provided the smoking gun. She studied the rotation curves of spiral galaxies and found something astonishing. In a galaxy, stars farther from the center should orbit more slowly, like planets in our solar system. But Rubin discovered that stars on the outskirts of galaxies were moving just as fast as those near the core. Again, the visible mass couldn't account for this behavior. There had to be something else, some invisible mass creating additional gravity. Rubin's work confirmed Zwicky's dark matter and sparked a revolution in cosmology. Today, we know that dark matter makes up about 27% of the universe. It doesn't emit light, absorb it, or reflect it. It's invisible across the entire electromagnetic spectrum. Yet its gravitational influence is undeniable. Without dark matter, galaxies wouldn't hold together. Galaxy clusters wouldn't exist. The large-scale structure of the universe, the cosmic web, would never have formed. Dark matter is the scaffold of the cosmos. But what is it? That's where the mystery deepens. Dark matter isn't made of atoms, protons, neutrons, or electrons. It's not part of the periodic table. It doesn't interact with light or ordinary matter except through gravity. This makes it incredibly hard to detect. Scientists have proposed several candidates for dark matter particles, the most prominent being WIMPs, weakly interacting massive particles. These hypothetical particles are predicted by extensions of the standard model of particle physics, such as supersymmetry. If WIMPs exist, they would have mass and exert gravity, but rarely interact with regular matter, making them perfect candidates for dark matter. To find these elusive particles, scientists have built ultra-sensitive detectors deep underground, in mines, tunnels, and mountains, shielded from cosmic rays and background noise. Experiments like Lux Zeppelin and Xenon use enormous vats of liquid xenon to catch the rare moment a dark matter particle might bump into a xenon nucleus, releasing a tiny flash of light. But so far, the results have been inconclusive. Some experiments have seen faint hints of something, but nothing definitive. Another strategy is to create dark matter in high-energy particle collisions. At the Large Hadron Collider in CERN, scientists smash protons together at nearly the speed of light, searching for missing energy in the aftermath, a potential signature of dark matter particles escaping undetected. Yet once again, nothing has shown up. It's like chasing a ghost that always stays just out of reach. There's also the possibility that dark matter isn't a particle at all. Some physicists suggest it could be made of primordial black holes, tiny remnants from the early universe. Others explore exotic ideas like axions, extra dimensions, or modifications to gravity itself. Maybe Einstein's theory of general relativity breaks down at galactic scales. Maybe gravity is stronger than we think in the outskirts of galaxies. These are bold theories and they're being tested, but none have unseated the dark matter hypothesis. Meanwhile, astronomers continue to map the universe with ever greater precision. By studying gravitational lensing, the bending of light around massive objects, we can create dark matter maps. Light from distant galaxies gets distorted as it passes through the gravitational fields of dark matter, revealing the hidden skeleton of the cosmos. These observations confirm that dark matter isn't just sprinkled randomly, it forms vast halos around galaxies and strings connecting galaxy clusters, forming a giant cosmic web. Dark matter also plays a critical role in the early universe. After the Big Bang, ordinary matter was hot, energetic, and scattered. But dark matter, immune to radiation, began to clump together through gravity. These clumps served as the seeds for galaxy formation. Without dark matter, the universe would still be a featureless fog. There would be no stars, no galaxies, no life. And yet we're still in the dark, literally. We've mapped dark matter's effects, but not its essence. It's one of the biggest unsolved mysteries in science. And it's not alone. Alongside it, another invisible force, dark energy, pushes the universe to expand faster and faster. Together, dark matter and dark energy account for 95% of the universe. What we know, the stars, the planets, the atoms that make up you and me, is just a cosmic afterthought. The search for dark matter isn't just about physics. It's a philosophical quest. It forces us to confront the limits of human perception. We like to believe that we understand the world, that science reveals the truth. But dark matter reminds us that reality is bigger, stranger, and more elusive than we ever imagined. There are realms we cannot touch, forces we cannot feel, and particles that may pass through our bodies every second, leaving no trace. And yet we keep searching, because every clue we find brings us closer to understanding the true nature of the universe. And in that journey we uncover not just the secrets of space, but the deep questions about what it means to exist in a cosmos that hides more than it reveals. If dark matter is everywhere, why can't we feel it? Why doesn't it weigh us down, light up our detectors, or alter our everyday experience? The unsettling answer is, it might be passing through you right now. Billions of dark matter particles streaming through your body every second without leaving a single trace. And that's not science fiction. It's current scientific consensus. Dark matter doesn't interact with your atoms. It doesn't collide, it doesn't stick, and it doesn't scatter. It simply flows, unnoticed. This raises a profound challenge. How do you study something that refuses to be seen, touched, or caught? Imagine trying to understand the ocean by studying ripples on the surface without ever diving in. That's where we are with dark matter. We see its gravitational wake, how it bends light, holds galaxies together, affects cosmic microwave background radiation, but the substance itself remains a ghost. Yet scientists are relentless. One approach gaining traction is indirect detection. Instead of trying to catch dark matter directly, researchers look for its fingerprints, specifically the energy signatures it might leave when it annihilates or decays. Some models suggest that when two dark matter particles meet, they annihilate into gamma rays or neutrinos. Instruments like the Fermi Gamma Ray Space Telescope scan the center of our galaxy for unexplained gamma emissions, possibly a sign of dark matter interactions. The galactic center is packed with stars and black holes, so the data is noisy, but there have been intriguing hints. Another strategy: searching for cosmic rays produced by dark matter interactions. Experiments like AMS-02 aboard the International Space Station collect high-energy particles from space, hoping to catch an anomaly that can't be explained by standard astrophysical sources. These methods are indirect, yes, but they broaden the net. Then there's the idea of dark sectors. Just as the standard model contains a zoo of particles, quarks, leptons, bosons, some physicists propose a mirror version for dark matter. In this view, dark matter could be more than a single particle. It could be an entire hidden world. Dark photons, dark atoms, even dark chemistry. These entities wouldn't interact with normal matter, but might interact with each other. Imagine an entire parallel physics playing out invisibly, governed by its own rules and forces. Some even speculate that dark matter could harbor structures, perhaps even life, utterly alien to us, yet coexisting within the same space. This may sound speculative, but it's grounded in real physics. The Standard Model is known to be incomplete. It doesn't account for gravity, doesn't explain neutrino mass, and can't integrate dark matter or dark energy. So physicists look to new frameworks: supersymmetry, string theory, extra dimensions, and beyond. These theories naturally predict new particles, many of which could be dark matter candidates. In recent years, some of the excitement has turned toward ultralight particles. While WIMPs have long dominated the conversation, newer models suggest that dark matter might consist of particles a trillion times lighter than electrons, like axions or fuzzy dark matter. These would behave more like a field than discrete particles, influencing matter on galactic scales with wave-like properties. Such a discovery would revolutionize our understanding not just of cosmology, but of the quantum world itself. But the most powerful tool we have in this search is gravity. Gravity is the only force that dark matter undeniably interacts with. And gravity, though weak, accumulates across vast distances. That's why one of the most promising ways to map dark matter is through gravitational lensing. When light from distant galaxies passes through massive regions of space, it bends, warped by the gravity of whatever lies between. This creates distortions, arcs, and smears in our images of the cosmos. By analyzing these patterns statistically across millions of galaxies, astronomers can reconstruct where the invisible mass resides. The Dark Energy Survey and the upcoming Vera C. Rubin Observatory are pushing this method to new heights. By scanning billions of galaxies, they'll map dark matter with unprecedented precision, tracing the hidden scaffolding of the universe. These maps don't just tell us where dark matter is, they also show how it evolved. Comparing early universe observations from the cosmic microwave background with present-day structures allows us to test models of how dark matter behaves over time. This leads us to one of the biggest scientific questions of all. Could dark matter be the key to a grand unification of physics? In the past, great leaps in science have come from explaining anomalies. The orbit of Mercury didn't match Newton's predictions. Einstein's theory of general relativity resolved it. The emission lines of hydrogen puzzled physicists. Quantum mechanics provided the answer. Today, dark matter is our great anomaly. It's the universe's way of whispering that our theories are incomplete. And it's not just a whisper, it's a shout. Because the consequences of understanding dark matter go far beyond physics. If we identify its true nature, it could unlock new energy sources, lead to entirely new technologies, even change our view of life and intelligence in the universe. Perhaps the reason we haven't heard from alien civilizations is because they operate on a level of physics we can't yet see, one rooted in dark matter interactions. Perhaps the next revolution in technology will come not from manipulating atoms, but from tapping into the dark universe. There's also a more existential perspective. Dark matter reminds us that we are not the center of the cosmos, not even close. The matter we're made of, the stars we admire, the light we see, it's all a minority. We're passengers in a universe ruled by forces and materials utterly foreign to us. And yet, we exist. We question. We search. And that, perhaps, is the ultimate triumph of human consciousness. To look into the void and ask, what else is there? To imagine the unseen. To build detectors in the dark. To chase the shadows that bind the stars. It may take decades or centuries, but the discovery of dark matter could be the next great turning point in our story. Because in the silence of space there is an echo. In the invisible there is presence. And in the darkness there is matter. If dark matter is the invisible glue of the cosmos, then dark energy is its silent accelerator. While dark matter pulls galaxies together, dark energy pushes the universe apart. These two forces, opposites in behavior, yet equally elusive, form the dark side of the universe. Together they make up about 95% of everything. Normal matter? The stars, planets, galaxies, and you. Just a rounding error. About 5%. That's it. This imbalance isn't just numerically shocking, it's philosophically disorienting. For centuries we believed that what we could see and touch was all there was. But modern cosmology has flipped that assumption. The visible universe is just the tip of a vast, dark iceberg. And we're only beginning to understand its shape. Let's dig deeper into why dark matter matters. Without it, galaxies would fly apart, literally. When astronomers measure how fast stars orbit the center of a galaxy, they find something strange. The outer stars are moving much faster than they should be. According to Newtonian physics, these stars should be flung into space, but they're not. Something is holding them in. Something with mass, something invisible. That's dark matter. But its influence doesn't stop there. In galaxy clusters, individual galaxies move as if embedded in a deeper gravitational well. The hot gas between galaxies emits X-rays, which also reveal an unseen gravitational influence. Even at the largest scales, the cosmic web, the filamentary structure of the universe, is shaped by dark matter's presence. Simulations that model the formation of galaxies over billions of years simply don't work without it. Remove dark matter and the universe collapses into chaos. So the evidence is overwhelming. Dark matter exists, or at least something playing its role does. But the question remains, what is it? Let's explore the main candidates. First, WIMPs, weakly interacting massive particles. These have been the favored explanation for decades. They're hypothetical particles that only interact through gravity and the weak nuclear force. They would have been created in abundance during the Big Bang and would still be drifting through the cosmos today. Experiments like Lux Zeppelin and Xenon T are built deep underground to detect the rare collision between a WIMP and an atomic nucleus. So far they've found nothing, but the search continues. Then there are axions. Ultralight particles propose to solve a different problem in particle physics, the strong CP problem. But as a bonus, axions could also make up dark matter. Unlike WIMPs, they don't bump into nuclei. Instead, they might subtly alter electromagnetic fields. Instruments like ADMX use powerful magnetic fields and ultrasensitive microwave cavities to try and catch a whisper of axions. Again, no confirmed detections yet. Some researchers are exploring even wilder ideas. What if dark matter isn't made of particles at all? What if it's a manifestation of modified gravity? This is the idea behind MOND, modified Newtonian dynamics. According to MOND, the laws of gravity change at very low accelerations, like those in galactic outskirts. In this framework, there's no need for dark matter, just a tweak in gravity. While MOND can explain some galactic phenomena, it struggles with others, especially at cosmological scales. Most physicists favor dark matter over modified gravity, but the debate remains alive. Let's not forget primordial black holes. These are black holes formed in the earliest moments after the Big Bang, not from collapsing stars, but from density fluctuations in the infant universe. If they exist in the right size and number, they could make up dark matter. But surveys looking for microlensing events, where these black holes would briefly magnify background stars, have found little evidence. Still, the hypothesis isn't fully ruled out. But maybe the problem isn't the candidate. Maybe it's our perspective. What if dark matter is something fundamentally new, not just a hidden particle, but a signal that our understanding of physics is incomplete? Just like the discovery of Neptune was prompted by anomalies in Uranus's orbit, maybe dark matter is pointing us toward a deeper layer of reality. This brings us to a speculative frontier, extra dimensions. In some string theory models, particles can propagate in higher dimensions. What we perceive as missing mass could be the gravitational shadow of particles moving in these unseen realms. It's a mind-bending idea, but one that's being explored at places like CERN. And what if we go further? What if dark matter is not only real but conscious? Some thinkers have proposed panpsychic models where consciousness is a fundamental aspect of all matter, including dark matter. While this remains entirely speculative and outside mainstream science, it reflects a growing openness to radically new ideas. After all, dark matter already breaks the rules. Who's to say what other rules it might be bending? From a technological perspective, identifying dark matter could lead to revolutionary advances. Just as understanding electricity unlocked the modern world, understanding dark matter might open pathways to new forms of energy, propulsion, or communication. Imagine harnessing the gravitational interactions of dark matter fields. Imagine using its properties to manipulate space-time. It sounds like science fiction, but every great leap starts with imagination. And then there's the anthropic angle. Some physicists argue that if dark matter were slightly different, more massive, more interactive, or less stable, then the universe as we know it wouldn't exist. Galaxies wouldn't form, stars wouldn't shine, life wouldn't emerge. In this view, we're not just observing dark matter, we owe our existence to it. We live in a universe that permits life precisely because the dark sector behaves the way it does. This idea feeds into the multiverse hypothesis. If there are countless universes, each with different physical constants, then we find ourselves in one where dark matter is just right. Not because of design, but because of selection. We're here to ask the question because this universe supports the questioners. Ultimately, the search for dark matter is not just about particles or physics. It's about the boundaries of knowledge. It's about pushing past what we can see to uncover what holds the cosmos together. It's about asking questions that may not have answers, yet asking them anyway. Because in the darkness there is structure, in the silence there is motion, and in the invisible there may lie the keys to the universe.